So the remainder theorem is said to be that when a polynomial fx is divided by ax minus b, the remainder must be f b over a. And b and a are constants, so b over a is a constant. And f b over a must be another constant. This is happening because we can write fx to be qx ax minus b plus rx. And this is happening when the degree of fx is bigger than or equal to 1, which is the degree of ax minus b. Otherwise, it's not working. And a must be not zero. A be non-zero guarantees two things. Firstly, b over a must exist. Secondly, the degree of ax minus b is 1, not 0. We need the degree of ax minus b because if the polynomial's degree is 0, or let's say smaller than ax minus b, the remainder is just polynomial itself and is not a constant, so it's not fixed. But why Rx must be f b over a? We can write the formula again and find out. So the degree of Rx, which is the remainder, must be smaller than ax minus b, right? And ax minus b is of degree 1, so Rx degree is 0. 0 degree is a constant, so Rx is a constant. A constant is always itself, doesn't matter what x is. So we can give x a special number, that is x is equal to b over a. Because if x is of b over a, then fx is 0 times something plus c. Then f b over a is c, and we know c, so we know c for all x. And this leads to another useful formula, which can help us to test if fx is divisible by ax minus b. If rx is 0, of course we can see that fx by definition is divisible by ax minus b. But Rx for all fx divided by ax minus b, we know the formula Rx is f b over a. So we can just put in x is equal to b over a, and we can test if this f b over a is 0. If it's 0, then we know the answer. We can get many other theorems from the remainder theorem, like x minus a must be a factor of xn minus an when n is a positive integer, and x plus a must be a factor of x to nth power plus a to nth power if n is an odd number. And another might be a bit complicated. If px is of degree n, and we still have ax minus b, and if px is divisible by ax minus b, It means that if A and B are relatively prime, A must be a factor of AN, and B must be a factor of A0 when we write Px to be in the form of an xn plus an minus 1 xn minus 1 until A0. The polynomial remainder theorem has a rich history that reflects the evolution of mathematical thought. The origins of this theorem can be traced back to ancient mathematical practices, particularly in the work of the 12th century mathematician Al-Samawa. Al-Samawa is credited with describing the polynomial division algorithm, which is closely related to the principles underlying the polynomial remainder theorem. In Western mathematics, the formalization of polynomial division and related theorems gained prominence during the 17th and 18th centuries. Mathematicians like Etienne Bezout contributed significantly to this area, and theorem is sometimes referred to as Little Bezout's theorem in his honor. The polynomial remainder theorem serves as a foundation for more advanced concepts, including the factor theorem. These theorems are instrumental in polynomial factorization and have applications in various fields such as coding theorem and numerical analysis. Understanding the historical development of the polynomial remainder theorems offers insight into progression of algebra and the collaborative nature of mathematical discovery across different cultures and eras.